So moving on to the last example, and this is where you will really see that why this differential idea is a lot useful. So now example 5 is talking about use the differential to estimate the amount of paint needed to apply one coat of not point. Make sure you change that, one coat of paint, right? That is 0.05 centimeter thick to a hemisphere dome that had with the diameter of 50 centimeter. So we are trying to estimate what is the volume of the paint that we need before we even start computing. So here's a picture of what we are looking at. Here's a atmosphere, and with this hemisphere, we know that this diameter is 50. So we know that the radius is 25, and we are trying to apply a coat of paint on top of this atmosphere. So that basically talking about the thickness of this paint right here, right? It must be, the given part right here, the thickness must be 0.05 centimeter. So to apply that, paint, and what is the volume that we need? So far, what we know is, we know the diameter, that is 25 centimeter. And this little, extra part, that is basically talking about the R, okay? So the differential of R, which is going to be 0.05 centimeter. So now the question is, do we remember, okay, the volume of a sphere? So here's a recall. The volume of a sphere is 4/3 pi r to the third power. So now with this, since we are talking about hemisphere, our volume is only half of this. So we are talking about the volume is equal to 2/3 pi r squared. So to estimate, right, the volume of this thickness that we need, right, we want to use the differentials. So we can talk about the differentials of volume V, that is equal to 2/3 pi times the derivative of r squared, which is going to be 2r.
I think it's r cubed.
Times dr.
Isn't it r cubed?
Oh, r cubed. Thank you. So I made a mistake right here. R cubed. So this will become cube and then 3 and a square. Thank you. Copied it wrong. So now, if I simplify a little bit, that will become the differential of V, that is equal to 2 pi, right, r squared times with dr. So notice that this formula, this differential formula, will help us to estimate for any thickness that we want for this particular diameter, or any other diameter that we're going to talk about later on, right? So those are the variables that we have. So that's why I mentioned it before. This differentials of V, in this case the volume, is depending on the diameter of the hemisphere with the dr, which is the thickness of the paint that you want to put it on. So now I can approximate the differential of V with respect to r equal to 25 and then dr equal to 0.05. So which will help me to do the computation of 2 pi times with 25 squared times with 0.05. So approximately, this will give us if we use a calculator, right? And that will give me approximately 196.35 centimeter cube. So now we found out that, right, the volume that needs to be um, by, right, to have one coat of the paint with the thickness of 0.05. So now the interpretation, final interpretation will be uh, approximately needed 197 centimeter cube of paint. And that concludes my problem in this case. Now, this approximation, is that right or not? We can easily find that out, right? By looking at the actual value. So what is the actual value? We want to find out the volume of that little blue line that I draw, right? That means we want to find out the volume of the hemisphere with you know the radius of 25.05. That's the whole thing, minus the volume of 25, which is before you paint it. And the difference in this y value, that should be close to this differential that we found out approximations. Okay? Because that's very close, because we only want 0.05 thickness. So what is the approximations of this value right here? Right? So plug it in this into the volume functions right here, and then computing it and then subtracting it, that will give me approximately 196.74 centimeter cube. So you can see that the approximation values are very close. Right?